Swayam Prabha. Digital India. Educated India.
Okay, in today's class we look at the analytical solution to a problem where more than one dimension is involved. In steady state, in conduction, so you can have situations where temperature okay. The first will be a transient conduction where your lumped capacitance cannot be used and your semi infinite assumption also cannot be used, and temperature is a function of both the spatial and the temporal coordinates. I mean it is a function of the spatial coordinate as well as the time. There is also a possibility where the temperature is a function of two spatial coordinates. So we can see that this represents an increasing complexity level. So once you go to temperature is a function of three spatial coordinates and time, and these spatial coordinates could be in the Cartesian coordinate, cylindrical coordinate or spherical coordinate. Beyond a certain level it becomes extremely difficult to solve it analytically. Okay, that is why numerical methods have been developed, but still many of these problems are tractable using analytical methods. Before the advent of computers, the PC came only in the 80s. Before the advent of computers, lot of mathematicians, applied mathematicians and even heat transfer scientists like Professor Ozisik, they have spent a lot of time in applied maths and they have tried to get analytical solutions to these problems. How far they are relevant today we do not know, but yet it is elegant because the temperature is found at every point in time and every point in space. If it is a numerical method, you can make your grid, you can choose your grid such that you can get a temperature at any point, but you will not get a closed form solution. You will not get an analytical expression wherein if you supply x, y, z and t directly it will give the temperature, okay, and there is still some elegance involved in this. Now needless to say we will be considering this. These are the easiest problems and it is good for communication, it is for the teacher also, it is easy for the student to follow this. This you can see that the asymptotic variations, the asymptotic variants of this problem where you do not really worry about the spatial dependence of time is basically called the lumped capacitance of temperature, is the lumped capacitance method. The other is the semi infinite problem where the thermal disturbance is only in the first few millimeters, or the first few layers, or the first few millimeters of the body. For example, if this is 10 centimeter, so in the early regime so if this body is at Ti and suddenly the temperature is brought to Ts, in the early regime a large portion of the body will still be at Ti, okay. Therefore some special techniques can be used. You can define a similarity variable, convert the partial differential equation into an ordinary differential equation and get a solution. okay, that is much easier than solving the full partial differential equation. The other thing is the late regime where the whole body can be assumed to be at one temperature, and then you can work out the Bio number. If it is less than 0.1 you can use that assumption, and then temperature is found to be dependent only on the spatial coordinate. In terms of dimensionless quantities, the non-dimensional temperature is just a function of Bio number and Fourier number. Okay, for all the other cases non-dimensional temperature will be a temperature of Bio number, Fourier number and x by L or r by RC, okay, r by r naught, where r is the radial coordinate, r naught is the radius of the cylinder of the sphere, as may be the case. Now let us look at temperature as a function of two spatial coordinates in Cartesian coordinates. So we look at the Laplace equation. Typically the problem could be like this. We take a rectangular slab which is infinite in the direction perpendicular to the plane of the paper, and typically it has dimensions L, W. Now I could have a prescription of temperature for simplicity. The three sides except the top are at a temperature Tc, Tc meaning cold temperature. The top I don't need to have a constant temperature. I don't need to have a constant temperature. I can have T as a function of x, which could be because of some heating, electrical heating or something. Okay, that is I can have, which means I can have something like this. The T can locally vary with x. Okay. Now the coordinate system is like this. Zero is here. Okay. So when do we get this two dimensional problem? When can we consider this two dimensional conduction? Basically if the slab is infinitely deep in the direction perpendicular to the plane of the paper, and it is bathed on three sides by a very cold fluid with a high heat transfer coefficient, you can assume that the three sides take on the temperature of the surrounding, take on the temperature of the fluid stream which is bathing this. Otherwise it is possible to have the general Robin boundary condition or mixed boundary condition of H and T infinity, which can also be used, which can also be tackled using the method of separation of variables, but that is going to be little more involved, right. And this is a precursor to many problems, the two dimensional steady state conduction. Okay, it has got ramifications. For example, if there is a heat generation, okay, you can have conduction with the heat generation, nuclear reactors and so on, or if there is a chemical reaction which is taking place. So the first step is the considering the Laplace equation, then if you add the heat generation term it becomes the Poisson's equation and so on. Now let us consider two dimensional steady state, constant properties, no volumetric heat generation. So the governing equation for this problem, which we have derived in an earlier class where we looked at the general three dimensional heat conduction equation, you can remove unnecessary terms, that is it is steady state, therefore unsteady term goes, the heat generation term goes, the body is stationary, you can remove all those terms. So you will be left with this is called the Laplace equation. So in compact form you can write this as the same. Okay. Now we want to solve this analytically using a very powerful technique called the method of separation of variables. Okay. The method of separation of variables starts like this. We first assume a product solution. That is, the t is a function of x into function of y. This is possible if you have a linear partial differential equations and all the boundary conditions are homogeneous. I will little later I will explain to you what this homogeneous boundary condition means, but this is a linear partial differential equation, right. But if you had terms like t dou t square by dou x, so dou x square, then is out, this method of separation of variables will not work. Okay, there is a difference. If you have x squared into d square t by dx squared, that is not a non-linear partial differential equation, that is a partial differential equation with variable coefficients. But if you have t into dou square t by dou x square plus, that is gone, then it is a non-linear partial differential equation. So we first assume that a product solution exists and then do what? Now once you have a product solution, it is possible for us to get dt by dx. So in order to be consistent, y is the solution and small y is the variable. Okay, please make this, as you will have, okay, small y is the variable coordinate and y is the solution. Yeah, couldn't read anything. Okay, so this is 3. Now I can have, you want to call it 3, no, we will do this. So d square t by dx squared will be equal to correct. Similarly, is it small x? Now we can substitute for d square t by dx squared and d square t by dy squared from equations 3 and 4 into equation 1. What do we get? Correct. Okay. Is it clear up to this stage? Now look at equation 5. Equation 5 is very interesting because the left hand side is completely a function of x, the right hand side is completely a function of y. So if a function which is only a function of x must be equal to a function which is completely a function of y, each of this must be equal to a constant, otherwise this will not hold good in general. Therefore we say that this must be equal to lambda square. Now doubt arises, why should it be lambda square? plus lambda square, it can be minus lambda square. There can be two doubts, why should it be plus, why not minus, and why are you taking it as lambda square instead of lambda. I am taking it as lambda square basically for convenience. Lambda is a parameter, okay, lambda is a constant, I can choose lambda or lambda square, lambda cube depending on my convenience. I know if I choose it as lambda square, I will get it in a form which is very convenient for me to handle, okay. It is plus because of the boundary conditions, which will become clear in a few minutes, okay. Now can we solve? Now we now have two ordinary differential equations. So the dou squared t dou x squared dou squared t dou y squared became d squared x dA, because we made a very major assumption that t can be written as a product of x into product of y. That is possible for linear partial differential equation with homogeneous boundary conditions. What this homogeneous is, I will come to it. Now we can solve this. Okay. Okay, 7 can be rewritten as eight can be rewritten as now if you put it as minus lambda square, what happens to this? What is the solution to that? E raised to, okay. Now let us look at the boundary conditions. Here it is Tc, here it is Tc, here it is Tc, here it is some f of x, assume that it is uniform. Now do you expect the temperature profile to be symmetric about x? Final temperature should be symmetric because left side right side boundary condition is the same, but whereas the top of f of x is hot, the bottom is cold, you expect the temperature distribution to exponentially decay in the y direction. If it has to decay in the y direction, you should get an exponential form of the solution in the y direction, and you should get a periodic form of the solution in the x direction. Therefore what we will do is nothing, no problem, I can change the minus here, okay. Now let us look at this problem. Left side is T cold, right side is T cold, bottom is T cold. Let us forget about f of x, it is hot. If it is hot, let us say this is, for the time being it is TH, T hot. How do you think the temperature at in this direction at any section, how do you think the temperature will decrease? The temperature will decrease exponentially. If you have something like this is like the Finn equation, d squared theta by d minus m squared theta. Finn equation gives an exponential variation, but therefore if I put this minus here, I am getting an exponential variation in x which is unphysical, because if this is 100, this is 0 0 0, I expect that this is the center at any point here. If it is 60 degrees, here also it should be 60 degrees. I do not want an exponential variation in the x direction, that is the wrong physics, okay. Or I could have made an argument that I keep the minus here, but I want to use minus lambda square, okay. Now therefore I make this plus, I make this minus, is that clear? Okay. Now what is the solution to 9? Very good. So No, I do not like cos first, I will have sine. So, the solution to 10 is if you have forgotten your basic calculus, it is good to substitute these back, we will do that, okay. So, dx by because the solution is a sin lambda x. So, if you multiply it by lambda square you get a lambda square sin lambda x, you get here minus a lambda square sin x, here sin lambda x, you get b lambda square cos lambda x, where here it is minus. So, here you get plus b lambda squared minus plus b lambda squared cos lambda x, here you get minus b lambda squared. Therefore, the that is correct. So, therefore, x equal to a sin lambda x plus b cos lambda x is indeed the solution to this ODE. So, we will keep that at as 11 as 11. By using an exactly similar procedure it can be proved that the solution to equation 10 is indeed what I have written on the board, that also we will check. No, this has to be small y, huh? Please note that cos h lambda y is e to the power of lambda y, okay, e to the power of lambda y plus e to the power of minus lambda y divided by 2. d by dy of cos h lambda will be sin h lambda. Similarly, d by dy of sin h lambda will be cos h, no interchange of minus plus sign, that but will not come for the hyperbolic. In fact, therefore, when we change, please look here, when we change the minus from this to this, we were talking about an exponential solution, but I am not taking an exponential solution, I am taking a hyperbolic solution, is that correct? Hyperbolic is already exponential, it has got, it is a linear combination of the exponential terms, e to the power of mx and e to the power of minus mx. Why am I saying e to the power of minus mx? We are so, I am so obsessed with fin heat transfer. So, that m is root of hp by k, so theta by theta b is e to the power of minus mx or cos h mx L minus x divided by cos h ml. So, therefore, this is like this. So, d squared y minus, huh? So, we are on firm wicket now, we have got the general solution to the problem. Obviously, it is an elliptic equation, because from the method of characteristics you can prove that b squared minus 4 is e less than equal to 0, greater than equal to 0, equal to 0. You can figure out whether a partial differential equation is elliptic, parabolic or hyperbolic, then once you have established it's elliptic, because it is second order in x and second order in y, it supports 2 boundary conditions in x and 2 boundary conditions in y. So you require 4 boundary conditions for closing the problem mathematically. The 4 boundary conditions are indeed specified on the 4 sides, whereas the left, right and the bottom are at Tc, the top is at a temperature of Fx. Therefore the 4 boundary conditions are specified, the problem is mathematically closed, it is possible for us to completely solve this problem. We have 4 boundary conditions. If you apply these 4 boundary conditions, you have got 4 constants a, b, c, d, you can straight away evaluate it and get a, b, c, d and you can get the solution. But so far it is very easy, but getting a, b, c, d is indeed the trick in the method of separation of variables. So far it looks so simple, the general solution is so easy, but when you want to attack and get the constant, you will have to invoke some higher mathematics. You have to know, you have to just get into orthogonal function, the property of orthogonality and all that we will see, alright. Therefore yeah, what is the equation number 13? Okay. Now these are the boundary conditions on the variable T, where T is the temperature. Now let me define. Okay, so 0, 0, 0, correct. You can, if you want, you can say T top equal to T top of x. Okay, therefore instead of if T minus T is equal to theta, okay, so this solution will also be a solution. Instead of T, if you define theta, it will also be a solution, except that A, B, C, D will get adjusted, because after all Tc is a constant, okay, because dt by dx is the same as d theta by dx, okay. So therefore theta is the general solution is now this is x equal to 0, this is x equal to L, this is y is equal to 0, this is y is equal to, what is the height of the plate? W. Correct. Should I draw it there or? and x equal to 0, theta equal to 0. This is for all y, which means everywhere x equal to 0 is like x equal to 0, x equal to 0.1 L, x equal to 0.3 L, 0.5 L, 0.6, 0.7, x equal to 1 L. X equal to 0 means this vertical line. So at all y this has to be valid. X equal to 0 means leave this C and D are untouched, go here. X equal to 0 means sin of 0 is 0, okay. Cos of 0 unfortunately is 1. Therefore at x equal to 0, theta is equal to 0 means theta equal to B. Therefore B equal to 0, correct. Alright. If B is not 0, we are having problem because cos of 0 is 1. If only that B is 0, sin lambda of 0, sin of 0 is 0, first two terms will 0, second term whatever we substitute value of y, whatever be C and D, always theta will become 0. So it satisfies the boundary condition. This is the homogeneous boundary condition I am saying. It is not possible to solve this equation for TC, TC, TC and this. The method of separation of variables can handle only one inhomogeneity. That is why homogeneous means very crudely first or Dirichlet boundary condition we make it equal to 0. Therefore I am defining a new theta T minus TC such that 0 0 0 0 0 0 I am making on the three sides, therefore I can do some magic like this, okay, because I cannot invoke many of these things if it is not 0. The method of separation of variables, the numerical technique will work, okay. So in the method of separation of variables, for example, if you have a problem where this is 100, 45, 35, 25, okay, so I will divide, I will subtract some 25, okay, and then make it into an equivalent problem. Then if three of the boundaries are having a temperature not equal to 0, then I will split the problem into 3 or 4. In each of these problems I allow only one wall to be at a temperature greater than 0, that is called superposition. Otherwise this technique will not work, because you can appreciate that because I am out of A, B, C, D I am keeping on cancelling something. This is not possible if I do not have the 0 boundary condition, it will become very messy for me, okay. Now therefore B equal to 0. Next, now at y equal to 0, theta equal to 0 for all x, what is that? That is the bottom wall. Okay. Now anyway, before this we will just write the solution. B is equal, okay. Please use small y here, sometimes I am not consistent, be careful, okay. At y equal to 0, theta is again 0, this is for all x. So you do not have to worry about A sin lambda x, for any value of x it should work, A cannot be 0. If A is also 0, then there is no problem, we have to go home. B is already 0, if A already 0, theta is 0 everywhere, then where is the problem? A cannot be 0, okay. So theta is equal to 0, it means that A cannot be 0, it should be valid for any value of x. And what is sin h of 0? 0. Therefore C can take any value, C is a free bird, but D cos h of 0 equal to 1, cos h is equal to 1, but theta has to be 0, okay, for any value of x, therefore D must be 0, correct. for all x. Therefore, (14, 15). Now the challenge is to get the product of AC. Is that all? You can call A into C as E. Is that all? You have to get the from the boundary condition. You have got two boundary conditions. Is there only one constant to find? You have to find lambda also. You have to find the value of lambda also. So two more boundary conditions are there. So with those two boundary conditions we can find the product of AC as well as lambda. Now let us do this. It becomes slowly more and more difficult. At x equal to L, for all y, theta equal to, very good. So this I can call it E. Okay. So theta is equal to E into sin lambda x into sin h lambda y. This is the general solution. 0 is equal to E into sin lambda L into that sin h any for any y. This is now, I am substituting x equal to L here, I am leaving this here. Now again theta equal to 0. If E is equal to 0, again everything becomes 0. If E is 0, temperature is 0, and that is trivial solution, it is not a solution to the problem. E cannot be 0, it should be valid for any value of y. So this cannot be made 0 because y is a variable in the problem. Therefore sin lambda L must be 0. This unfortunately is satisfied by a infinite succession of values, okay, where lambda is given by n pi, okay. So therefore n pi by L, sin 0, sin 180, sin 360, sin 540, sin 720 all are 0, okay, where n varies from which one? Yes. So it is satisfied by 0, 1, 2, 3 and so on. Okay. But 0 we do not include, 0 will create some gudbad. So next step will now there is a property theorem which says that in such a situation when lambda, there is a succession of values of lambda each of which satisfies that sin lambda L equal to 0, the general solution is given by a summation of all these solutions, okay. Therefore sigma Any problem? N sin h or I can replace this by please note you won't get sin nh n sin h n pi y by w you won't get, because lambda is coming basically because the lambda is coming because of the L, because it is a periodic boundary condition in L. In W it is a exponentially decaying function. Yeah, it will be where it can be satisfied. Why should the E1 be equal to E2 be E3? Okay, so the E is a constant. Since it is satisfied by succession of values, I can't make a fatal assumption that everything is only one E. There is a E1, E2, E3, E4. Therefore, this is the solution to the problem. This is an infinite series. Now we started with so very simple way it started, now it has come to this stage. Now to get this En, we have to substitute the last boundary condition, that is at the top there is a non-homogeneity. That can be anything. No, not linear. What? No, that can be anything. But it can be a general f. It can be periodic. It can be a sinusoidal function or a cosine function and all. I am just giving for a general f of x. Okay, but I am going to reduce it for a special case where it is only one temperature. Okay. As you, if it is non-uniform, it is exponentially decaying, then we are in trouble. It should be symmetric about the center. That is understood. That is coming from the physics. Now we substitute the last boundary condition. So fx minus Tc okay. So this is invariably this is specified to you in the beginning of the problem. You know what this value is. It can also be a constant value. It could be just Th minus Tc. It could be 50 degrees, or for a problem in which you make this is T top, T left, T right, T bottom. I can make theta is equal to T minus Tc, so I can make this as so this could be just that 70, that left side is known. Sin h n pi w, I will tell you what the value of w is. You know what is L. If it is a square slab, w by L is equal to 1. N is nothing from 1, 2, 3, 4 into infinity. Okay, but this boundary condition is valid for all values of x from 0 to L. So if it is constructed in this way, is there a way to find out En? What is the problem? Is there a way to find En? So with if you do not know what is orthogonality, you are stuck here, you cannot proceed further. We have to invoke the property of orthogonality, which we will see in the next class, but before that I will give you a sneak peek of what this orthogonality all is. You know that sin x and cos x are periodic functions, okay. So lot of mathematicians have done research on expressing any function as a sum of sine, as a sine series or cosine series. So if any function f of x can be expressed as a sine series or cosine series, this f of x minus tc can also be expressed as a sine series or cosine series. If it is possible for us to represent it as a sine series, already there is a sign which is coming here, with that there is hope for us to find En. Do not worry about this sin n pi h pi w, that is just a constant. You can make En into sin h n pi w by bel is En dash, E dash of n, okay. Now that orthogonality property where any function can be represented as a sine series or a cosine series, okay, this is called the Fourier series, okay. So this is the Fourier series. So from the property of Fourier series we have to get the value of En, which we will do in the next class.